Okay, let us start. So last time what we see is we talk about predictor corrector method, right? So we see predictor corrector methods, right? So predictor is a method which predicts uh, initial value in the fixed point iteration, and then corrector is the method which do the computation, right? And then what we see is we see predictor, evaluator, and then corrector method, right? PEC method, where we predict and then evaluate and then correct, right? And then we see this. So what we do is we predict and then evaluate and then correct and iterate up to certain points, and then finally we talk about this and then evaluation again, right? So these are the four types of predictor corrector methods which we talk about in our previous lectures, right? So we see how we can predict by using an explicit method, and then evaluate to apply the implicit method, and then uh, again rotating or repeating the process iteratively, evaluating and evaluating and iterating, and then we end up after evaluating the final term. So that's how this method study is being done. And then we see an example of how we can do this predictor evaluation correction method, right? By using elementary or first order Euler methods, explicit and implicit as well. Similarly, you can do for any other explicit and implicit method. The very important thing is the predictor must be an explicit method and corrector must be an implicit method, right? If that is not the case, then the predictor corrector thing does not comes into consideration, because actually this comes in whenever we are trying to solve a method by using an implicit method. To have the initial value, we use the prediction method. So then a couple of classes before that, we talk about uh, absolute stability, right? So we talk about stability and then we talk about absolute stability. So we have seen this, right? So we see that we define a Q, which is H line lambda, with lambda belongs to complex number, right? So we define a value which is Q, which is basically a complex number, right? And then we talk about a stability polynomial. You remember, right? So we talk about phi of Q comma Z, right? Which is rho of Z minus uh, Q times rho lambda times. So yes, so what we did is this. It's a rho Z minus Q times sigma Z. Right, so we call it stability polynomial. Right, so we call it stability polynomial, right? And then we see that, right? The roots basically, right? So we see that the root condition actually implies the absolute stability, right? So that is something we studied when we talk about absolute stability of a linear multi-step method, right? So this is for linear multi-step method. We studied absolute stability like this. So today what we are going to do is we are going to combine this with this, right? Predict the correct method and absolute stability. So what we are going to do is we are going to combine all of them and combine both of them and try to establish a absolute stability condition for the predictor, evaluator, corrector method, right? So and so the absolute stability of the predictor corrector mode. Right, so you know that they are all linear multi-step method. Basically, it is a combination of two linear multi-step methods, right? Right. So if the numerical solution we apply, we obtain by applying the predictor corrector method, whatever the predictor corrector method it is, right, to the standard first order differential equation y prime is equal to lambda y, right, then this bounded, then we call it as a stable method, absolutely stable method, right? And then the region is obviously right? So the region at which the method is absolutely stable is called the stability region, right? So that's almost similar to the definition we studied for absolutely stable, but the only difference is there we apply the linear multi-step method for this differential equation. Here we are applying the predictor corrector method for the differential equation. So you know that now we have two different methods, right? So two different linear multi-step methods here associated with this. So we have to incorporate all of them. Right? So we will see how we can do that, right? By again looking at the same example where we use Euler method as the predictor and corrector method as well, right? So explicit and implicit. So let's do an example. Okay, so we take predictor method as explicit Euler method and then implicit Euler method as the corrector method. So let us do that. Let us write down how we are doing that. Just PEC, right? So there is only one prediction and one correction. So there is no more computation, just one computation. So where you compute y1 initial value y1 0 and then you compute y1 1. So there are only two computations. So that is okay. Let me explain this first and then write it down. Okay, so this is how we do, right? So you have explicit Euler method as the initial prediction method and implicit Euler method as the correction method. So these are the predictor methods, right? So y n plus 1 is equal to yn plus h times f of tn comma yn is your prediction and correction is yn plus 1 is equal to yn plus h times f of tn comma yn plus 1, right? So this is your corrector method, right? So this is the standard notation we use for explicit Euler and implicit Euler. Right? So now let's see what we are doing in computation. Right? So assume that so first let me write down this. So let me see what we do in computation, right? Right. So this is what we do. We take the previously computed value yn, right, and then we compute yn0 using the predictor method, and then we compute yn plus 1 as the approximated value for, right, y at tn plus 1, right, by using that corrector method, right. So where yn plus 1 is considered as an approximation for capital Y at tn plus 1. And so this is how this predictor corrector method goes, right? When you are doing computation, this is what you do. At some point, right, at each step, you take the previously computed value, right, and then compute the initial value for the present computation, and then you iterate one time to get an approximation for this. So you know that at the end of this step, this is your solution you have. So you obviously know what you have here, right? Right, so this is the important thing, because in order to avoid confusion in the notation which I am going to use in the derivation of the absolute stability, right? So you should not get confused with the notations, right? So you know that at each step, 1 is the superscript you are going to have for the approximation, right? But to get 1, you need to get a 0. To get a 0, you need the previously computed value. So the previously computed value should be yn1, right? So that is the notation which I am going to use here, right? So whenever I am using yn1, you should know that it is the previously computed value, and yn plus 0 is the intermediate value which we have by using the predictor method, and yn plus 1 is the computed value or the approximation at this step, right? So that is how my notation is going to be in this computation, right? So then this is how I can rewrite my predictor notation, right? So here now you can see the notation. So Okay, so this is why I am using the notation. Right? So now the explanations given to you explains why I am using these notations, right? So because of the way we do computations. Okay, so now by looking at this, we can start writing down our problems, right? So right, so if you write P, the predictor method, you get yn plus 1 0 is equal to yn1, right, plus h times f, but f is lambda times y. That is how the question is given, right? H is lambda times y. So that is how the predictor method looks like, right? So then obviously you know h lambda is q, right? So you have right, so you have yn plus 1 is equal to 1 plus q times yn 1, right? So that is what you have as the predictor method, right? So now we have to use the corrector, right? And the corrector method says yn plus 1 1 is equal to yn1 plus h times f is lambda yn plus 1 0. Right? So that is how you have the corrector method. Right? So yn plus 1 1 is equal to yn 1 plus h times f is lambda times y. So here y is yn plus 1 0. So that is how your corrector method looks like. So now you can substitute for yn plus 1 0 here. Okay, so we can substitute for yn plus 1 0 here. H lambda is q, right? H lambda is q, and then yn plus 1 0 is this. yn1. Okay, so this is okay. So if you simplify this, you get yn plus 1 1 is equal to 1 plus q square times yn plus 1. So now you can see that the way we are dealing with the absolute stability is different from what we learned in the previous step, right? Because in the previous cases or in the last class, what we did is we just write the stability polynomial, right? Phi of q comma z, which is rho of z minus q times sigma of z. Here you have a problem because you have two methods. So you cannot write down a stability polynomial straight away. So what you do is you apply the definition, direct definition. That is when you apply the problem or method to y prime is equal to lambda y, we get a solution, and that solution should be bounded. Right? So here, what you see that yn plus 1 is equal to 1 plus q square times yn1. That is the method which we have now, right? So when you combine predictor and corrector methods, this is an equation you have. Right? So you know that you are talking about boundedness. So let's take the absolute value. Right? So this is true for all n. Absolute value of yn plus 1 is equal to absolute value of 1 plus q okay, so this is true for now. If this value is less or equal to q, sorry 1, if 1 plus q squared is less or equal to 1, right? So then you know that yn plus 1 is less or equal to yn1 for all n equal to 0, 1, 2, and so on. Right? So if this is less than 1, then this is true. And if this is true, then you can get this, right? So yn plus yn1 is less or equal to yn minus 1, 1. Right? It's less or equal to y naught 1. Right? So you can get this relationship. Yn, if this is true for all n, then yn1 is less or equal to yn minus 1, 1, n minus 2, 1, n minus 3, 1, all the way up to 0, 1. But this is the initial value, right? 0, 1 is the initial value, which is fixed. Right? Right, so clearly y naught 1 is the initial value, and that one is fixed, right? Because initial value is always fixed. So if this is fixed, this absolute value, fixed value, so yn1 is bounded by some fixed value, right? It's a fixed positive value. So that means the sequence of iterations is bounded, right? So that is the definition we see for absolute stability, right? So this boundedness condition holds only if this inequality holds. Right? So we can summarize this. right? So then you can summarize this as, if this condition is true, then the method is absolutely stable. So now you can simplify this condition, right? So that is another problem where you simplify the condition and look for the stability region, right? So okay, so now if you want to find the region, so this will be the region, right? So Q, all Q satisfying this inequality gives you a region on which the method is absolutely stable, right? So you see that the on the Q plane, the region of absolute stability is the region on which the method is absolutely stable. So we have proven that if this condition is true, or this condition holds, then the method is absolutely stable. So you can verify, or you can try to find the region if it is if it is okay to find it, right? So not all the inequalities are solvable, right? So at least at dual level. So here we will try to see at least the boundary. So at the boundary, you know, the absolute value should be equal to 1. So you ended up with two cases, right? So one is plus 1, one is minus 1, right? So in both cases, you can see the region. Just these are just extra computations, right? So okay, so here you can see that, right? So if this is equal to 1, right, that boundary is gives you q is equal to 0 and q is equal to minus 1, right? And then this gives you two complex roots, right? So minus b plus or minus b squared minus 4ac. It's this, right? So you know this actually gives you q squared plus q plus 2 is equal to 0. So you ended up with -1 plus or minus square root of 7 over 2, right? So you can see these complex numbers, right? So these are what, minus here plus square root of 7 I and minus here minus square root of 7 I, right? So you can draw these regions in a complex plane and figure out what are the possible values for absolute stability, right? So these are boundaries, and then you can draw them and you can figure out the boundaries as well, right? So the Q which satisfies all these four conditions leads you to the boundary, and or basically if this interval is if this inequality is true, then the method is absolutely stable, right? So these are just extra computations which you can do to see the absolute stability of the method, right? So that is how we uh, find the absolute stability. So here you can notice that we find absolute stability in a different way, right? We don't use the characteristic polynomials here, right? That is very important, because for a linear multi-step method, because it is only one method, you can always use the characteristic polynomials as well, right? The first characteristic polynomial and the second characteristic polynomial. But when it comes to predictor corrector method or predictor evaluator corrector method or whatever it is, right? You cannot use the characteristic polynomials because there are two methods involved in the PC model. Right? One is predictor equation or multi-step method and corrector multi-step method. So one of them is explicit and one of them is implicit. So it is not possible to use the characteristic polynomial method. So we go back to the basic definition. The basic definition for absolute stability is as long as the method is stable, the computed values are bounded. Right? The sequence of computed values are bounded for all n. So you look for that boundedness condition and then try to develop stability condition based on that. Or there is another way of getting the boundary, right? So here I just do the regular mathematical calculation, right? So just solving an absolute value equation and then getting the roots and things like that because it is easy. Sometimes you may use the boundary locus method also, right? So as a homework, I will ask you to do the thing, right? Right? You can try the boundary locus method as well. So now let me give you a couple of more examples. Okay, so here, this is the important thing, right? So because it is a predictor, evaluator, corrector method, right? So that is the difference between predictor corrector and predictor evaluator corrector. Very minute difference, but you should notice this, right? Because you know that in the predictor evaluator corrector, here first in predictor you compute this, right? And then you evaluate this, and then you compute this, and that is what you do: predict, evaluate, compute. Correct, right? So that is what you do. Right? You are given this, so you compute this, you evaluate this, you evaluate this, right? But remember, if I am writing the explicit Euler method correctly, I should put 1 here, right? So in the previous step, in the previous example, there I put 1. But the reason I am not putting 1 here is because when you are doing a real computation, right, you do not compute this at any step, because here you can see that you do not compute by Tn, sorry, Tn plus 1. Huh? So Ytn plus 1 and Yn plus 1, Y1 you don't compute, because that is not necessary for you. You only compute Y naught, right? F at Y naught is the only thing you compute. F at Y1 you don't compute, right? You do that only when you have a E at the end, right? If you have E at the end, then you would have computed, right? If not, you don't need to compute that, right? So then you don't have to compute Y1 here for the prediction method. You can still use the previously computed value. So that is why there is a slight difference here from the predictor corrector method, right? So because of this evaluation and because of this term is different, and that is very important for you. You should see that, right? So in the predictor, that is a big difference, and because of that big difference, you are going to have a different way of getting a polynomial, or right, to get the absolute stability region, you will have a different type of condition, right? So as an exercise, you can try working on this and try to develop the results, right? So in the tomorrow class, we will talk about another chapter which is called Rankuta method, right? So I will leave this one as an exercise, but this is very important. The way I use Yn naught is very important. When you are doing computation also, you have to keep that in, right? So I will stop here and then continue in the next class.